All right, here we go again. Now we're going to talk about stoichiometry and how that's used for molarity. Hang on just one second. Okay, so we're going to talk here about stoichiometry and how that relates to molarity. They like to, sort of scramble these questions together on the AP exam. So if they ask you a stoichiometry question, that also requires you to do a molarity problem for the first step. So it's not that difficult. It's just kind of an extra step on your stoichiometry, which I'm sure you're grateful for. So an example of that might be something like this. How many grams of CaOH2 are needed to neutralize 25 milliliters of 0.1 molar HNO3? Well, there's a lot going on here. First of all, we are doing stoichiometry because we're talking about a chemical reaction that's happening. Okay, this is not a dilution. This is not just asking you to calculate molarity. This is actually talking about a neutralization. This is an acid-base reaction, okay, which we know how to write the equation for an acid-base reaction. And on your stoichiometry, I would just stick with the molecular equation. That's usually the easiest. You don't have to worry about writing net ionics when you're doing stoichiometry, okay? That's just on the equation writing section. And it just works better for you if you stick with the molecular equation when you're doing your stoichiometry. So first thing you always need in stoichiometry is a balanced chemical equation, okay? So we've got CaOH2, and we are adding that to the HNO3 to neutralize it, the nitric acid. And so this is a strong acid and a strong base, and you know that this is a strong acid, HNO3, because you have memorized the strong acids, okay? And so you should end up making water and a salt here, which is going to be calcium nitrate, CaNO3 okay? And then we just need to make sure this thing is balanced, which I think putting a 2 here and a 2 in front of our H2O should do it. Okay, so now we've got our balanced chemical equation, and we've got 25 milliliters of 0.1 molar HNO3. Well, initially that doesn't seem to help us that much. What we need really is moles of HNO3, but remember, molarity equals moles over liters, so if they're giving us the molarity and they're giving us the volume, then we can find the number of moles, okay? And they'll do this often, so you need to get used to this kind of calculation because it happens a lot on the AP exam. So our molarity is 0.100 molar here. And our volume, again, you have to be careful. This is in milliliters, so we need to move this decimal over 1, 2, 3 places to the left. It's going to be 0.0250 liters. Okay? And so the number of moles of this that we have, the HNO3, is going to be a small number, 0.00250 moles. Okay? So now we have a starting point, and then you can just do your normal stoichiometry here. And they're asking us for grams of CaOH2. So we start with 0.00250 moles of the HNO3. And we have to go from moles of HNO3 to moles of the calcium hydroxide. And based on our balanced chemical equation, this is a 1 to 2 ratio here, okay? And then once we have moles of CaOH2, then we just go from moles back to grams, okay? And calcium is about 40, I think 40.1, 40.08. Here, I'll actually use all the numbers this time. Plus 32, plus 2. Well, I'll sort of use all the numbers. 74.08 grams. Okay? And so then once we calculate all this out, we should get 0.0926. Looks like we need 3 sig figs here. Grams of the calcium hydroxide, which is not very much. But that looks reasonable based on the small number of moles that we had to begin with. It doesn't take a lot to neutralize all of that. Okay, so that's how the stoichiometry problems tend to work. Titration, we have already talked about that. Titration, essentially, you've already done that. You basically just, use an unknown, usually a base, to titrate an unknown acid. Now, it can go the other way. You can use an acid to titrate a base too. Usually when we do titrations in the lab, we're going to titrate an acid with a base, because then you get to watch it change pink instead of it starting pink and you having to watch it change clear. That's not quite as much fun. But that's how this works, okay? And some definitions here, just so you know. Standard solution, that's the one that we know the concentration of, okay? Equivalence point, that's the point where you have now added, however many moles of acid you had, you have now added that many moles of the base to it, okay? And so that's your equivalence point, okay? Now, with a strong acid, strong base, equivalence point is going to happen at pH 7. We're going to talk more about that later in the year. With a strong acid and a weak base, or a weak acid and a strong base, it's not that way. Or with a weak acid and a weak base. The end point, that's the point where the indicator changes color. So the phenolphthalein actually changes color around pH of 8, which you guys probably saw this from your lab the other day. So the equivalence point happened at 7. Our indicator changed pH, or changed color at pH of 8, which that sort of shows you that you don't want to just use the indicator. If you're trying to be very precise with your lab, that's why we had the pH meters as well, so we could see exactly what the pH was and when. Because if you assumed you were at the equivalence point at pH 7, you would have been close, but you might have been just a little bit off. Now, you guys probably noticed that if you've done your graph at this point, it kind of goes like this. Okay, so probably your pH, you would have been off by, a tiny, tiny, tiny amount if you had just used the indicator to find your equivalence point. But, sometimes those tiny amounts count. And then an indicator, like phenolphthalein, it's just a dye that changes color in different pHs, and you've used different ones of those. I don't know if you use cabbage juice in biology or not, but cabbage juice is a pretty good indicator. pH paper, phenolphthalein, there's lots of different indicators that will, change color and show you approximately what the pH of the solution is. So that's the phenolphthalein titration that you guys already did. Alright, here's a sample problem, and this is a little bit tricky. And this will be probably the last one that we do. I may skip this last one just for the sake of time. So we've got Cl minus chloride ions in a water supply. And sometimes you can figure out how much chlorine is in there, how much chloride is in there, by adding some silver to it and seeing how much silver chloride precipitates. Okay, so how many grams of chloride ions are in a sample of the water if 20.2 milliliters of 0.1 molar Ag? I'm just reading the question. I don't need to do that. So it's telling us how much Ag plus we need to react with all the chloride in the sample. Okay, now this is not much different than the last one that we just did. But essentially what they're telling us here is how much of the Ag plus that needed to be added. 20.2 milliliters of it, and we knew the concentration. Okay, we've got a balanced chemical equation already. That's kind of nice. We don't have to worry about that. So all we have to do here is use our molarity equation to figure out how many moles of Ag plus we actually added here. So moles divided by liters. And again, have to be a little bit careful here. 0.100 molar is equal to moles over liters of solution. So we have to move the decimal point 3 places over. 0.0202 liters. And so our number of moles of Ag plus is going to be equal to 0.00202 moles. Okay? And we need to know how many grams of the chloride ions are in there. I'm going to leave myself a lot of room here. I may have to take this to the next line here. So moles of Ag plus, So what we know, we've got to go to moles of Cl minus first. And in this equation, it's a 1-to-1 ratio, so not totally necessary step here. But then we can go from moles of the chloride ion back to grams of chloride ions. So moles of Cl minus over grams of Cl minus, okay? And now this is just one chloride ion we're talking about here. We want to know the mass of one of them, or 1 mole of them, I guess. And so this is not diatomic, okay? You got to be a little careful there. So this is 35.453 grams of chloride in 1 mole. And then when we calculate all this out, this ends up being 0.07, how many sig figs here? 3. 0.0716 grams of chloride ions in the sample of the water, okay? It doesn't even tell us how much water there is. It doesn't really matter. We don't need that to be able to figure this out, okay? So that's an example of a titration that's not an acid-base titration, but it's the same basic thing. We're adding a certain number of moles of silver until we have completely reacted all the chloride. And the way we know that is, then once we start adding more silver, no more of the AgCl forms. So that means the chloride must have all been used up at that point. Okay? So that's how that works. Now, if the sample has a mass of 10 grams, what percent of chloride ions does it contain? Okay, we just figured out how many grams we have here. 0.0716. So if we want to know the percent of chloride by mass in that compound, we just divide it by the total sample, which is 10.0 grams. We times that by 100. Oops. So that's, okay, really should have been able to do that in my head. You're all laughing at me right now. 0.716%, which is not very much, which is probably a good thing. We don't want too many chloride ions in our drinking water. They're good for killing little bacteria, but they're also, in high enough concentrations, they're good for killing us. So we want a low percentage there, but that's how they figure out what percent of your water is actually chloride ions. Okay, and like I said, I think we're going to go ahead and skip this one for now. You guys can try that one if you want. It's really, let's see, is there anything tricky about this one that you wouldn't know? I mean, essentially what you're doing here, you need to write a chemical equation first. This is a strong acid and strong base reaction, okay? Which I guess we can at least do that part of it. So the NaOH plus the H2SO4 gives us Na2SO4 plus H2O. And then you balance this thing, and I think, again, that will do it. Then you have your balanced chemical equation. So basically what you have to do here is 45.7 milliliters of the 0.5 molar H2SO4. You would use that to get to moles of H2SO4. And you know the volume of the NaOH solution, so you can figure out the number of moles of NaOH that you have. Okay? Once you figure out the moles of NaOH that you have, then you take moles divided by liters, because they tell you the volume of the sample, and that will give you the molarity, the concentration. Okay? So hopefully that makes sense. I don't think I need to go over that one. You can ask me about that one in class if you want to. So that's it for the molarity calculations and stuff. It's basically just adding one extra little step on the top of our stoichiometry that we've already done. So there's not a lot to it there, as long as you know that molarity equation. Okay? All right. We will see you in class. I don't know who we is. I will see you in class.